All right, everybody. We're going to talk today a little bit about what derivatives are graphically. What exactly is the relationship between, reminder, f of x is presumed to be a function where f prime of x we will refer to as the derivative. And there's a relationship, of course, between derivative and slope. As a reminder, f of x equals some number that is the output of the function, whereas f prime of x, this represents not really a value of itself, it represents a rate of change, or what we're going to really talk about is slope. Okay? So, graphically speaking, let's just take a look at a particular function. And we're going to do some samples, and we're going to turn this function, and actually, let me pick a different color, just so we can express that. So here's a nice red. We'll go up and down and back up again. So this is our function we'll call f of x. And I want to point out, I'm not going to tell you what it is, but graphically, we just want to kind of explain it. And we want to explain it using maybe a secondary graph, f prime of x. So how do we go from an original function, f of x, to its derivative is really what we want to take a look at. So there's many ways to do this. I like to do a simple, maybe not so simple, but a sort of two-step method is one, pick a point on f of x. We'll do so. I'll say, look, let's choose this point right here. Okay? What are we going to do with that point? We're going to draw the tangent line. As a reminder, a tangent line is a line that only touches the graph at one point, sort of maybe something like that. So we have this green tangent line, and unfortunately there is a step 3. The slope of the tangent line is the y value of f prime. Okay? So, what does that mean for us? Well, that means that wherever this function on f of x, what it achieves at this particular x input, that slope value, I'll estimate to be somewhat positive. I'll put a small dot there. Okay. Now, as you're going to see, this is going to look different based on other points. So now we just repeat the process. Let's pick another point. Let's go right at the origin. Okay. There's our point. Let's create a tangent line. So this tangent line is actually going to go slightly underneath. And the whole point is that this line, again, I don't know the exact slope, but you know what I do know? I know it's negative. So maybe something like that. Let's pick another point. In fact, let's pick a point in the middle. Let's say maybe right here. Notice at that point, we get a really flat tangent line, or a tangent line whose slope is near 0. And so, if we just kind of start doing the connection game, one thing that you'll notice is maybe the slope, think about going from this point A to this point B to this point C. Let's think about what the slope is doing. So the slope is going from positive down to negative. The slope is decreasing. Then the slope is further decreasing until we get to C. Now, what's going to happen after C? Well, we'll pick some more points. Let's maybe pick a point D right there. And one thing that you'll notice is, yes, close to 0, maybe a little positive. So that gives us another point that maybe it'll turn and it'll start heading upwards. Now, if you sample more points, you can get a better idea of the graph, but I might say that this function in red has the following in blue. And, this can kind of be like my first sketch. I'm going to do a much better sketch just based on what I know. So here's what I know. I know that the slope starts off very, very positive. And it ends very, very positive. And down in the middle, it's going to switch over to, a slope of 0. Then it'll keep going. So that's how we can relate functions to their derivatives, graphically speaking. Okay? Let's do maybe a slightly easier one. One of the easiest ones to do is something like a piecewise graph. So maybe we'll have something like this. And I want to point out, these are all supposed to be straight lines. So, once again, this is f of x. Can we come up with f prime of x? Okay, so what is the slope of this line? Well, if you draw a tangent line to a straight line, you get the actual line itself. So it's the same thing as asking what's the slope of this line. And maybe I don't know, but I do know it's positive. And the whole point is that it's going to have the exact same slope all the way through it. So its derivative function is constant. Okay? Up till a certain point. And maybe I should match these up just a little closer. So it'll be constant. And then what happens? We make this jump, and suddenly, what is the value of the slope of the tangent line? Well, the tangent line is going to have a constant negative slope. This is an example where I want to point out f of x is not continuous. F prime of x is also not continuous. As it turns out, if your function is not continuous, your derivative cannot be continuous. But that's not the whole story. There's actually something slightly more interesting going on. I'm just going to move to the right real quick. Okay? Now, the following function that I'm going to draw is continuous. And we can see that it's continuous, and this is a really important point called a cusp. And the important point of this is that a cusp is sharp. Okay? It's a sharp point on the graph. Unfortunately, that's going to cause some problems for our derivative. Now, why would that cause problems? Well, reminder, we want to estimate the tangent to these curves. Let me pick a different color than blue. We'll go red. So here's f prime. So starts off, slope, very, very flat. We'll say it's very, very close to 0. Then it's the slope. Imagine these tangent lines. They get more and more and more negative. More and more and more negative. More and more and more negative. So we see this sort of behavior heading towards that. Now, what happens immediately after that? Suddenly, we're all positive. There are positive slopes. And then they sort of fade out to 0. So then suddenly we're positive, and we fade out to 0. And what's curious is that f of x is continuous, but f prime of x is not continuous. So, we can summarize this as such. Number one, if f of x is not continuous, then f prime of x is also not continuous. Now, this is the second point. This is a little bit more challenging. If f of x is continuous, then f prime of x may or may not be continuous. And that's really, really interesting. So what do we need to be on the lookout for? Look out for sharpness, aka look out for these cusps. Okay? And again, what is a cusp? A cusp is a very firm point. So one of the more interesting graphs that is not what we call differentiably continuous, we have x, f of x equals the absolute value of x, or you can think about it as the square root of x squared. So what does that graph look like? Well, if you've taken a pre-calculus class, hopefully you know it creates this V shape. And specifically, that V shape, not smooth. In fact, it's a sharp cusp. The problem is, what does the derivative look like? Well, the slope here is -1. The slope here is +1. So the real question is, what is the slope at 0? No clue. It's not something that we can define like this. And the whole point is, notice, this causes f prime of x to not be continuous. Okay? So, just because f is continuous, that does not imply, it doesn't inherit that continuity. Okay? But I can declaratively say, if f is not continuous, then f prime is also not continuous. Okay? That's an important distinction to make. Now, I did have, looking at your homework, I wanted to preview section 3.2. I just completed it myself. There was a question that I wanted to take a look at. A lot of these questions are marrying up some situations together. I wanted to talk about some difficult applications. I think those are the most important ones. So first of all, let's read this question, and then we'll decide what the answer is. A capacitor is a large device in an electrical circuit that stores charge. In one particular unit, the charge on the capacitor Q varies in time. And here's my hint. Anytime you're going to look at a graph, don't hit the make larger, although I will say that's not that bad. I prefer to hit this little pop out. I think that's just the best graph you're going to get. So what do we know about this measurement Q of capacitance? We can see that it starts very, very small. It shoots up, and then it levels out at some positive number. So the question is, when is the magnitude of the time rate of change of Q the greatest? Well, Q, this is a graph of Q, and we're going to transfer that down to our whiteboard. So as a reminder, what does Q look like as a function? We'll just kind of estimate it to look like that. I know we had some units on there. We want to do our same trick. We want to talk about Q prime. What is the rate of change? So again, what do? We take some small points. We estimate the slope, and we say that slope is very sloped. M is a large number. So maybe that means we're all the way up here. We keep taking more and more points, and we see the slope generally starts to decrease. So from that green graph Q, I expect this blue graph Q prime just based on, oh, this slope is slightly decreased in value, this slope is slightly decreased in value. It's sort of flattening out. Okay? So the question is, when is the greatest, as a reminder, Q measures rate of change, whereas Q is measuring our capacitance, which is measured in some electrical, excuse me, some electrical units that I'm not privy to. So, when is the rate of change? It's actually going to be at time equals 0. And the reason it's going to be at time equals 0 is because, again, we're not asking when does Q achieve its maximum value. Ooh, don't know what that did. When does Q achieve its maximum value? Which one is the rate of change of Q? Which, according to this, when is the slope the highest? And it seems like closer and closer to 0. Okay? Now, Q prime is blank for all t. And the options are positive, negative, or both positive and negative. So, as we start to, and I don't know why it keeps doing this every time I go back to it. As we start to, compare these two, we can see it's heading towards 0, but it's never actually going to equal 0 just because we're leveling off. Which tells me, notice, it's all the way above the x-axis. All of these lines are positive. As we get closer and closer to 0, we can say that they're still always going to be positive for t greater than or equal to 0. Now, what about Q prime? Is it an increasing or decreasing function? Well, Q starts higher on the left every piece it goes down. Q, I will go back to the original, is an increasing function. Yet, Q prime is a decreasing function. Because reminder, even though Q is getting larger, the capacitance is growing larger, the rate of change of that capacitance is slowing down. And so, as a metaphor, this is, oftentimes people use water as an idea of, or gases and fluids as an idea of capacitance. We'll call this our capacitor, right? And at t equals 0, I'm going to say it's empty. Now, how easy Q prime measures how quickly fluid, and in this case it's really electrical capacitance, flows. Okay? So I want you to think. Right now it's empty. So I just stick a little garden hose on, right? What does that garden hose do? It just comes out. Oh, it's so easy to add water to it. Okay? Then it starts to fill up. Okay? There's still plenty of room here. Starts to fill up. Starts to fill up. As it starts to fill up, it's harder and harder for me to put more water in it because the water is going to have to fight the water that's already in it. So even as I fill it up more and more and more, it's increasing. The rate of change is that it's slowing down in its increase. And that's a difficult concept to master. But this is what the language of derivatives is allowing us to talk about. We're not just talking about, well, what is the capacitance? We're talking about is how is that capacitance changing? In this case, we can say that Q prime is a decreasing function of time. Now, last but not least, which one looks like it? I think a better way to answer this question is to say, what exactly is going wrong with these? So, why don't I like this one? Well, this implies, if this is my graph of Q prime, this implies that the slope is starting off negative. And I got to go back to my function. I got to ask myself, are these tangent lines, are these lines with negative slope or positive slope? And I think the answer hopefully is clearly positive. So, I don't like A, I don't like B. Now, C or D. If we go to C, we see a positive slope, right? And that positive slope keeps on going. In fact, it gets more and more positive. It starts at essentially 0, and then it becomes very, very positive. Again, is that what we're seeing in Q? Do we see it slopes starting at 0, and then? No. So, by process of elimination, I think the only answer is D. So, what are the essential lessons that you need to learn from section 3.2? This is a bit of a smaller one, and I hope you guys recognize that. I would say the number one thing is make sure you're looking out for sharpness and cusps. That's really going to throw off these F primes. But as a reminder, F prime of A equals the slope of the tangent line on the curve f of a. So we have some function, we choose an a, the tangent line, which I'll put in green, technically olive, the slope m equals f prime of a. That is the fundamental Q. So, once again, I hope this helps. If you have any questions, let me know, and I'll see you all in the next video.